So this is the binomial hypotheses testing assessment, and we've got question 1. Africa works in a call centre. She assumes that calls are independent and knows from past experience that the probability of success is 1/6. She makes 9 sales calls. Calculate the probability that at least 3 of these calls will be successful. So for A, the first thing I can write down is I can say let X be the number of successful calls. We need to write that down. Then, because they're independent and they're a discrete variable, I can say that X is binomially distributed to the number of trials, well there were 9 calls, and the probability, and that's the same for each one, so again I know it's binomial. And I want at least 3, so I'm finding the probability of X being greater than or equal to 3, which is the same as 1 minus the probability of X being less than or equal to 2. All I have to do then is type that into my calculator and I'll get 0.1782 to 4 decimal places. B. The probability of Africa making a successful sales call is the same each day. Africa makes 9 sales calls on 5 different days. So now we're thinking about days. Calculate the probability that at least 3 of the sales calls will be successful on exactly 1 of the days. Okay, so we need a different variable now. We're going to say let Y be the number of days when Africa makes at least 3 successful calls. And we can say then that Y is binomially distributed. There are 5 days, so 5 trials. And the probability of at least 3 successful calls is what we worked out in part A, so 0.1782. We now want to calculate the probability that she does it on exactly 1 day, so when Y equals 1. So we type it in and we get 0.4061 to 4 decimal places. Okay, now we're going to have a look at C. So C says, Rowan works in the same call centre as Africa and he believes that he is a more successful salesperson. To check Rowan's belief, Africa monitors the next 35 sales calls Rowan makes and finds that 11 of them are successful. Stating your hypotheses clearly at a 5% level whether or not there is evidence to support Rowan's belief. So for C, we're going to again start by saying let X be the number of successful calls Rowan makes. And we're going to say our H0 then is the same probability as Africa. So that P was equal to 1/6. My alternative hypothesis, he thinks he's better, so I'm finding P is bigger than 1/6. Now we have to say, assume HO, assume the null hypothesis is true. Then X would be binomially distributed. There are 35 calls that she's monitoring. And we're saying that probability is true, so 1/6. And we want to find then, is him making 11 calls or more extreme enough for us to reject the null hypothesis? Does it give us a result that is significant enough that we can say, actually, it's not the same probability, he is making more calls? So the probability of X being greater than or equal to 11. And a good little check here we can do is this sign that we've used in our null hypothesis here should be the same as this, but with an extra line, an or equals to line. So we'll type that in and we'll get 0.0231 to 4 decimal places. And we are now going to compare that figure to this 5% significance level. It's a one-tailed test, so I'm just writing that as a decimal. I'm not halving it first. And that is less. So because it's less, it is significant. So it is a significant result. There is evidence for us to reject the null hypothesis. And we need to write, there is sufficient evidence to suggest Rowan is more successful. We never say that a hypothesis is definitely true. We're just saying it suggests, there's evidence to suggest it. Question 2. So what is meant by a 5% significant level? So that significant level is the probability of us rejecting the null hypothesis when it is actually true. So like in my question before, because that was less than 0.05, if actually, in reality, he isn't more successful, well, the chance of us incorrectly saying that he was is only 5%. So we'll write that down. It's the probability of rejecting the null hypothesis when the null hypothesis is true. Part B, what is meant by a p-value in the context of a hypothesis test? So the p-value is the probability of getting an outcome at least as extreme as the observed value when the null hypothesis is true. So the p-value is the probability of obtaining an outcome at least as extreme as the observed value when the null hypothesis is true. Question 3. The random variable x is binomially distributed with the number of trials is 50. The value of the probability p is unknown. Carly decides to conduct a hypothesis test at 5% significant level to investigate whether the value of p is less than 0.4. Identify the critical region for the test. Okay, so firstly, we're identifying the critical region for the test. So we are going to say x is binomially distributed, and we're going to assume that, sorry, this is playing up, the probability is actually 0.4. Okay, now we will say then, assume HO is true. So HO was that the probability was equal to 0.4, and the alternate hypothesis is that the probability is less than 0.4. So because it's less than, it means I'm only doing a one-tailed test, so I don't need to halve my significance level. Now, what I would do, because we don't really know what values to start at, and I can't just work out 50 values for the number of trials, we're going to see if it was true, how many would we expect to come up. So 50 times by 0.4 gives me 20. So that is my expected outcome if this were true. So we want to find some values that are definitely less than 20 to see if they are actually significant. So the first thing we will try is, I'm just going to try 5 less. It might not work, but I'm going to try x is less than or equal to 15. That gives me 0.0955. Well, that's greater than 0.05, so it's not significant. Okay, let's go a bit lower then. So let's try 12. That is 0.0113. Okay, that is significant. So now I'm going to have to check the one above. What about x is less than 13? That's 0.0280. Okay, so that's still significant. So let's just double check 14. That's 0.0540. Okay, so that is not significant. So my biggest value that is significant is 13. So that means that my critical region is going to be for x is less than or equal to 13, which means the acceptance region is going to be when x is greater than or equal to 14. Question 4. Freya and Alex are investigating the proportion of households in Ilkley that buy more wholemeal than white bread. A national report says 11% of the households in the country buy more bread than white bread, so 0. No, go away. 0.11. Freya and Alex survey 35 households and find 10 of them buy more wholemeal bread. Conduct a hypothesis test at a 1% significant level to investigate whether the proportion of households buying more wholemeal than white bread differs from the national proportion. So this means two-tail test, which also means that this 1% significant level of 0.01 needs to be halved, because I'm going to have half either side. 0.05 is what we are testing against. So we'll start off with our statement. Let x be the number of households that buy more wholemeal than white bread. We're going to say H0 is what we've got from the national report, 0.11, 11%. And the null hypothesis is that it does not equal 0.11. Remember, it said different, so I'm not doing more than or less than. We assume then HO is true. And we say X is binomially distributed. There are 35 households that were observed, and the probability is 0.11. Now, to determine if we're going to look less than or more than when we're finding our probabilities, we're going to find out the actual value that we found when we looked at these 35 households. Well, that was 10 out of 35. Which is equal to 0.28. Now, because that 0.28, my actual that we found, is greater than what we expected of 0.11, I'm going to be finding the probability that x is greater than or equal to 10. So, the probability of x being greater than or equal to 10 is the same as 1 minus the probability of x being less than or equal to 9, which on my calculator gives me 0.0035 to 4 decimal places. Now that we're going to compare to our significance level. Well, that's less than that, so that means it is significant. So we will reject HO and say there is sufficient evidence to suggest that the proportion of households that buy more wholemeal is different, don't say more than, different to 11%. Okay? Right, now, part B, it says, explain what assumption must be made about the 35 households surveyed for this to be valid. Well, we have to think about the conditions for a binomial distribution. And that is going to be that the households are independent of each other. Okay, so the households are independent of each other. C, explain why the true significance level of your test is unlikely to be exactly 1%. Well, it's because the binomial distribution values are discrete. So I can only look at exact numbers. So I can only look at 10 houses, 11 houses, 12 houses, 13 houses. And it's highly unlikely that when I work out the probability of one of those, let's say just for example, that is equal to exactly 0.01 or 0.005. And that is because 13 is a discrete number. If it was continuous, there will be a value because it is continuous. So we will write down binomial distribution is discrete, and so it is unlikely that any probability is exactly 0.01 and so it is unlikely to have an critical region of exactly 0.01. Okay, question 5. Each day Anna drives to work. R is the event of it raining. L is the event that Anna arrives to work late. You're given these probabilities. Determine if they're independent. Okay, so we're going to start off with a statement. If R and L are independent, then the probability of R times by the probability of L would be equal to the probability of R and L. So let's just see that. 0.36 times by 0.25. That gives me 0.09, which is not equal to the 0.2 that they gave me. So they are not independent. So because they're not independent, it means that we've got some overlap, which draws us on to part B, which says draw a Venn diagram. So my Venn diagram, we have to have a box around the outside as well. And I've got two circles. This one's R, this one's L. And the middle bit is the 0.2, the intersection. Now, the probability of R, we're told, was 0.36. So that means all of this circle, including the middle bit, has to add up to 0.36. So I need to firstly take away that 0.2 to see what's left over, which will give me 0.16. Same for L. So all of L added up to 0.25. So we're going to take away that 0.2 to leave me with what's left just in this section. And then the bit that people quite often forget, there should be some number outside. So we're going to add up what we've got, 0.16 plus 0.2 plus 0.05, which gives us 0.41, and then we're going to take that away from 1 to see we've got 0.59 left over.